So, good morning, everyone. Welcome back to the second day of this week of our summer school. And let's start the day with Professor Harald Pfeiffer's second lecture on spectral methods and their application to partial differential equations.
Yeah, good morning, everybody. Welcome back. Today, I'd like to start with some demonstrations, and especially coming back to yesterday's tutorial. I hear you all put a lot of effort into it, which is great. But I also hear that some of the pieces were quite unfamiliar. And I also need to apologize because since this course that I'm teaching here is actually the first time I'm doing this, and everything is newly developed, there were also some typos still in the problem set, which I'll briefly point out as well. So the problem set was about exploring Fourier spectral methods, and the actual code, as already said, is quite short. One of the functions to write was this real to Fourier, which once you figured out what's going on is basically a single call to a Python FFT routine. And then if you want the coefficients to be nice, you need to somehow rescale them a little bit in order to have the coefficients conform to it's really the coefficient of the exponential directly. Going back, the same. The function Fourier to real of some coefficients A, it can be done with an inverse Fourier transform call. And if you want to have nice meaning of the coefficients, we have rescaled the spectral coefficients up here. It turns out we also have to rescale when we're going back. If you don't insist on the coefficients matching one-to-one the sines and the cosine terms, but can be off by some multiplier, you can actually do away with these lines 15 and 25 here. So all of this is, once you've understood what's going on, remarkably simple, but writing these very short pieces of code is also remarkably difficult. The third function was let's take a derivative. So we go from the real space values u to the coefficients a of the sine and cosine expansion, or of the e to the ikj. And then when you go from when you take derivatives, you have your e to the ijk, and by e to the k ikx, and taking derivative moves down the I times k. And so the only thing is that we have to multiply the coefficients by the imaginary number times k. And then we can go back to real space values afterwards. Using these little pieces of code, we can then go off and actually do all the cool Fourier transform stuff we've talked about in class yesterday. So here's one example of doing that. I'm picking 32 grid points. Line 6 initializes the grid points from 0 to 2 pi without an endpoint. And here's the first problem we had. On the problem set, I had this function u1 still spelled out a little bit wrong. It had all the same features, except that it was a lot bigger than the other functions. And so here, what I'm doing is I'm evaluating this function at the grid points. X is a Python numpy array, so it contains all the points at once. And out comes u at all the grid points at once. Plotting it on the left-hand side, AX0. And so far, nothing really exciting has happened. And line 10 is where things get interesting. I'm calling our magic function that gives us the spectral coefficients from the real space values. So the C tilde now are the coefficients of the e to the ikx. And on the right hand, in the right plot, I'm putting down a plot of the C tilde, their absolute magnitudes, because they're complex numbers. And what comes out of this is shown here. On the left-hand side, our exponential of the cosine. The cosine is being put in there to make this thing really, truly periodic. And then on the right-hand side, here's 32 grid points. That gives us 17 coefficients. You see that these coefficients decay extremely rapidly, and as advertised, this is a log plot. The straight line here is indeed the exponential convergence we were looking for. Once you play this game with 4 functions, the plots begin to get overwhelmingly complicated. So I've put in a little plot function that does the common work. So I can call it 4 times for the 4 functions. And what comes out of this is, at the end of the day, a plot that looks very similar. The blue curve is the one I've just shown you. The fairly wide Gaussian, where with about 16 or 18 coefficients, you're down at 10 to the minus 16, and then you're hanging around round off. U2 is just a linear function. I've now rescaled it by dividing by 6, so that the magnitude, the absolute value of each curve is about 1. And I've also updated the problem set and fixed these typos from yesterday. And while U2 here looks really, really simple, its spectral coefficients behave very, very badly. They don't really become smaller at all, or not much. The same for U3, the parabola. Again, the coefficients are large. And U4 is another periodic function, because it is a function of cosine x only. But this time it is thinner, a sharper peak. And because it's still periodic and smooth, we see the exponential convergence. But because it has sharper features, we need more modes to reach a certain accuracy. So if you want to get to 10 to the minus 10, you would need about 14 modes of the blue curve, but about 24 modes of the red curve. So the sharper features your functions have, the more modes you're going to need to represent them. Not really surprising. Any questions about this so far? Or anything else from yesterday? Let's first get these awful curves up here a little bit out of the way. And let's repeat the same plot, except that I'm going to way higher resolution, 2000 points instead of 64 points. And that I'm using now a log scale on the right plot. And I'm only plotting U2 and U3, the 2 nasty ones, or the 2 strange ones, to illustrate better what's going on here. So, same plot as before. On the left-hand side are the 2 functions. On the right-hand side are their Fourier coefficients as a function of the coefficient number, but now a log-log plot. And now suddenly these seemingly constant curves actually begin to go down, and they go down as straight lines, because the U2, the coefficients decay like 1 over k. If you go to 1000, the coefficient number goes down by a factor of 1000. And the orange curve, the coefficients decay like 1 over k squared. We are at 10 to the minus 6 for coefficient 10 to the 3. And this, of course, is related to what I've explained yesterday. If functions are not continuous or not differentiable, then the degree of non-differentiability is manifesting itself in the convergence rate of the Fourier series. The functions look very continuous and smooth here on the left panel. But this is simply because I've chosen to put the singularity right at the edge. A Fourier series is completely repetitive, and the 0 to 2 pi integral is going to repeat itself between 2 pi and 4 pi and 4 pi and 6 pi. And so the overall function being represented here is more looking like this. And so you see this gigantic, enormous discontinuity right at the edge. For the second example, well, the function is parabolic, so it looks more like this. The second one is continuous, but it's not differentiable at these kinks down here. And so these decay rates of 1 over k and 1 over k squared actually fit together with what we discussed yesterday in class. The next part of the problem set is both really important, and it turns out more complicated than what my little instructions were making out. So this is about getting into the habit of monitoring how accurate your solutions actually are. Because you can do a numerical calculation. If you're not knowing how accurate it is, and if you're not aware that there's limitations, you can get total nonsense results out without knowing it. And this is a very unpleasant situation you don't want to find yourself in. So this problem was about various attempts of figuring out how to interpret how accurate a solution might be. The first error measure that I gave you is to take the highest coefficient of the expansion. So if we have an expansion like the one up here, that happily decays exponentially, you take the magnitude of this coefficient here, and because all the other ones are going to be exponentially smaller, that one should give you a fairly good indication of everything else you have disregarded. This has the nice feature that it's really simple to do. You just need the coefficients and you're done. There's one little difference I did here is that I put in the two highest coefficients instead of just the highest, because quite frequently, if you have symmetries in your problem, you have the situation that half your modes might be zero. Like yesterday, the A1 mode in this introductory example with axis symmetry. And if by some pure symmetry chance, your highest order mode happens to be zero, you don't want to go away claiming, oh, I have an infinite accuracy here, an infinite precision. No need to worry about anything. You could be totally wrong. So if you're taking two, you're almost certainly guarded against these types of symmetry problems. The next one is also quite useful, but a lot more difficult to do. If you want to do the difference to the solution at a lower resolution, you also have to compute the solution at the lower resolution, which you should always do. But then those two runs have different grid points, and so you need to interpolate one on top of the other. And so this is what's going on in these few lines here. Here I'm setting up my lower resolution, U low. I'm computing its Fourier coefficients. And now comes the annoying part, which is difficult to do if you, but becomes easier with more experience. I now need to sum up this U tilde low, the low resolution, at the collocation points of the higher resolution grid. There's nothing to be done for when you want to evaluate a series at other points than to do it. So you just have to bite the bullet. We know that un minus 4 of x is the sum of some c tilde e to the I kx. K goes from 0 to whatever the maximum value is. And if we want this at some unusual point, not at the grid points, well, the only thing we can do is actually sum up the stuff here on the right-hand side. And that's what this loop over the coefficient is doing for us. The Python enumerate gives me in J the actual number 0, 1, 2, 3, and in C the coefficient. And so here's the thing, C times exponent I times J times X. And I have forgotten to write down here that we also need the real part in our real Fourier series. And Python is actually counteracting my efforts here. Usually I'm using I or J for indices. And I've switched away from using I in the Fourier series and replaced it by J because the I is also the imaginary number. And now I use J as my summation variable. And guess what? Python uses J as the complex number. So one J is the complex number and the other J is my summation index. And then the next annoying thing that also comes up, this is specific to doing Fourier transforms, is that it actually turns out that the Python Fourier transform normalizes the 0th term differently by a factor of 2. And if you really want to sum up your series, you really need to perfectly know what your basis functions are and their conventions. Otherwise, these types of sums will not work out. Okay, at the end of the day, all of this works. And what we can do is we now have a solution at this lower resolution, which we can plot as a function of x. And we can also take the difference between low resolution and standard resolution. And this is also going to be, as we see in a little while, a good measure of how accurate the solutions actually are. The third one I asked you to do is, where's the third one? To take the difference of un and u at the grid points that seems like a nice thing to do because you have the grid points already, and if you just use them, then you're getting around all this complicated interpolation business here, which looks short but is quite tricky. The difficulty is that at the collocation points, the approximate solution is identical to the actual function we are going to solve for. And so what you're ending up is basically taking the sum of zeros. And so this isn't a useful thing to do. And the fourth measure is again using interpolation, but this time you're taking un on a finer grid. Let's not worry about this. This is another complicated piece of code. And let's look at the results that we have here. So what's here on the left side is I'm now solving the problem 5 times. And the blue curve here is this notion of I try to investigate how accurate we are by taking the highest coefficients. They happily go down, as they should. The second one is I compared solutions at 2 different resolutions. That gives you the orange curve, which is pretty similar. Looks a little bit worse, but not very much. The third one is absent because it's down at 0 and useless. And the fourth one is also pretty much in line with the other ones. So the bottom line here is all 3 of these things work out quite nicely when you want to evaluate how accurate your solution actually is. The last one, however, this one is good for educational purposes here in class, but you can't use it in practice because the solution that you're looking for, you don't know it. So you can't subtract it off. The blue one, however, this only depends on the things you calculate. And the orange one as well only depends on the things you calculate. So the blue and the orange ones, you can always compute from your solutions as well and use them to monitor how well things are. The right plot here is also very important. Let me simplify it because it's so busy that you're not seeing anything on it. Let's take that one away. This is a very typical plot one should be making. And you will see it as well more frequently in the rest of this course. So this is the UN minus 4 minus UN type calculation, where we take solutions at two different resolutions and take the difference to see whether our calculations become more and more accurate as we increase n. And for small n, you get the blue curve up there, and then those curves go down as they should. And the important thing to notice is that on a logarithmic plot here with the logarithmic y-axis, these curves go down approximately equally spaced if we keep on adding the same number of basis functions. This is again a reflection of the exponential convergence. Well, with every 4 more basis functions in this particular case, we are gaining about 1.5 orders of magnitude in accuracy, and so these lines are going to be equally spaced. And that's a really important feature to look out for when doing spectral calculations. And finally, I couldn't resist putting in a little bit on the Gibbs phenomenon. So we are back down to this function here. And what the right plot here shows is, let me first scale out. Here's my axis limit. What the right plot here shows is in red, really just the function x that we were trying to approximate. And then in the 3 colors, 3 times this type of series summed up at a very, very finely sampled grid, much finer than the collocation points of the underlying transformations. As you can see in the middle, everything looks quite nice. But as you go to the edge, this is where things go bad. So let me zoom in into the right edge here. And here, again, the red curve is the straight line that we are trying to approximate. And because the Fourier series is continuous, all the Fourier series expansions have to jump down to 0 to continue with the next sawtooth pattern here. And before they go down, they all overshoot by approximately the same amount. And that's what's called the Gibbs phenomenon, that Fourier series do this overshooting. And even if you increase resolution arbitrarily much, the overshooting is going to remain the same. It's just that it is compressed closer and closer to your point of the discontinuity. As an illustration that Fourier series are really not good to use for problems with discontinuities or non-smooth behavior. Okay, so much for a brief recap of the tutorial. And today's tutorial will continue along the same themes, so pretty much asking the same questions, but this time around for Chebyshev polynomials. The good thing about Chebyshev is that Stage 1, the FFTs aren't there, so this difficulty has fallen away. But stage 2, the way to compute derivatives involves a somewhat weird recurrence relation that can be coded, but that requires some very careful thinking. Okay. Let me switch back to Blackboard and actually continue finishing up 2 more details about Fourier series and convergence before then moving on to the Chebyshev series. So I'd like to begin by briefly highlighting here again the main features in these convergence plots that I was just highlighting in Python here. So here's again a plot of your favorite spectral coefficients as a function of number. The y-axis is always going to be log, but on this plot here, the x-axis is linear, and on the other plot over here to the right, I'm going to put things on a log-log axis. So for the good types of functions, where spectral methods are really the weapons of choice, you should expect the following behavior. That first, the coefficients are more or less constant for a more or less long period of time. And then they decay pretty much exponentially. And then if you're pushing resolution too hard, you end up with this feature that we also saw in some of these plots. And so to explain what all this is, the first part up here, this is the coefficients you need to actually resolve the broad features of your solution. And unless you have enough basis functions to actually get the broad shapes all correct, the coefficients won't really begin to decay much. Then we have our nice long, bigger font, okay. Then we have our nice long exponential convergence. And then ultimately, down here at around 10 to the minus 15, 10 to the minus 16, we are running into the numerical round off. So the simple fact that computers only represent numbers up to about 16 significant digits. For the bad functions, this plot more looks like this. So this would be the non-smooth functions. And this is a typical smooth one. And if you now turn over and go on a log-log scale, where you now can go up to much higher basis vectors k, the non-smooth functions turn into straight lines. So the coefficient goes like k to the minus whatever convergence order you have, convergence order. And but because the exponential ones decay so amazingly quickly, they typically only look like this on this type of plot, that they're compressed all the way to the left in the first 10 or 20 or so modes. Whereas in order to see the straight line behavior of the bad algebraic convergence, you need to go to hundreds of thousands of modes. Yeah.
Just tell us what the resolve plot.
Thank you for asking. So these first modes, we solve the broad features of U. And so the important naming convention is that k to the minus some power is called algebraic convergence. Whereas the one we care about, this one over here, this one is called exponential or geometric. I'm using the word exponential. The word exponential comes around because, well, our coefficients are somewhat have some scale like e to the minus mu n for some mu bigger than 0. And the geometric comes about because you can write this thing here as well as p to the n for p being e to the minus mu. And this is, well, this is a geometric series, p to the n. That's why some people call it geometric and others look at this formula, have that formula in mind, and call it exponential. I'm in the exponential camp, so I'm going to call this exponential convergence. Any questions about this? Okay, then I'd like to finish with one more detail for the Fourier series, which will bring the Fourier series into very nice conformity with what we're going to do with Chebyshev later on. And Fourier series as matrix multiplications. So if we have, let's start again with our magic formulas. Which I have on a different piece of paper here, so I need to go back. That the Fourier coefficient was 1 over n times the sum uj e to the ij, and I'm keeping the grid point here because this is good enough for my purposes. So I need a k here. Ck is, yes. So we have the coefficient is this formula here. And the point I wanted to make is that this is a matrix multiplication. So this is the same as writing S kj times uj sum over k, where skj, well, is simply 1 over n e to the I k xj. And I think I'm missing a minus sign here because we're going to the coefficients, and so we should have a minus sign. Yes, and indeed I have a minus sign in my notes as well. Conversely, we can go back to real space with similarly a matrix multiplication. So going back to real space was the sum over the spectral coefficients, e to the I k x j. Sorry?
Like sum over K or sum over J or K.
That sum is over J, thank you. And so similarly, if I go the way back, let me try again. Uj is the real part of the sum of ck tilde e to the I k xj. This is again a matrix multiplication, so I can write this as the real part of the sum of a matrix P J K C delta K, and the sum here is over K, and this P matrix, well, is just whatever is multiplying the CK, and this is a e to the I k xj. So we can go back and forth between real space and physical space by doing these matrix multiplications. And I've written them here with indices, but you could also now become, if you want to get a little bit more fancy, you could introduce a vector U that has all the U's, all the grid point values, and you make a vector C delta that has all the C deltas, and over 2 C tilde. And then you could write this as C delta equals matrix S U, and you can write it as U equals real part of matrix P times C delta. So you can go back and forth with matrix multiplications. And it turns out you can also write if you now combine these two things together with the other equation that we had, that the coefficient of the derivative is equal to ik times the coefficient of the original series. This is also a matrix multiplication. I can introduce a matrix D tilde as a diagonal matrix having the elements 0, I, 2i, whatever the largest k times I, and so forth. And then we have the situation where I can write the grid point values of the derivative. So this is going to be du dx at the xi. I can write these as I'm starting out with the grid point values itself. I'm first going to come to the coefficient space by multiplying with the S matrix. Then I'm going from my coefficients ck to the coefficients of the first derivative via this D matrix. Because it is diagonal, it only acts on each coefficient itself. And because the diagonal elements are the I times k, we are getting precisely what we want. And then I can go back to real space with the P matrix. By the way, the names S I chose for spectral coefficients and P for physical space. And we need a real space here as well, because we are still doing a Fourier series. And if I now go one step further and define a real space matrix T as the real part of P times D times S, then this whole condition up here boils down to a single multiplication by this matrix D to take derivatives. So we are in the situation that we can now compute derivatives at the grid points as one matrix multiplication times the data at the grid points itself. And once you have this differentiation matrix, the whole business of using spectral methods becomes yet simpler because, well, taking derivatives is literally just a matrix multiplication. And the really cool thing is, if you have chosen your grid points carefully, if you have gotten all the matrices right, this matrix multiplication still preserves all the incredible accuracy of the spectral methods, even if you only have a few grid points. Okay, no demo at this point. I will demo this when we get to the end with the Chebyshev polynomials. So let's now switch over to Chebyshev polynomials and the big question of what to do with non-periodic functions, because for better or worse, almost everything in our universe is non-periodic, especially in space, but unfortunately also in time. And the big thing we need for non-periodic functions are precisely our Chebyshev polynomials. So non-periodic functions. We work on the interval -1 to 1 now, because this turns out is the most convenient one for Chebyshev polynomials. And we are still trying to approximate and interpolate and work with a function u of x, but now in this interval -1 to 1 instead of 0 to 2 pi. And the Chebyshev polynomials have a very nice definition. One nice thing about the Chebyshev polynomials is that you can write them down and almost everything about them analytically. So you take the arc cos of your argument x, you multiply it by k, the number of the Chebyshev polynomial, and you take the cosine again of it. It doesn't look very much like a polynomial, but in fact it is. We have t0 equals 1, because cosine of 0 is 1. We have t1 equal x, because you take the cosine of the arc cos of x is x. And for t2, well, you end up with cosine of 2 theta, where theta is the arc cos of x. And now you can do trigonometric identities, and this is the same as 2 cosine squared of theta minus 1. But cosine of arc cos is precisely the x again, so this is x squared, is 2x squared minus 1. We can play the same game again for t3 and so forth. So for t3, well, this is cosine of 3 theta. Now the trig identity is that this is 4 cosine cubed minus 3 cosine of theta. And so t3 is going to be 4x cubed minus 3x. What you're already seeing here is a Chebyshev polynomial k has an x to the k in it. So it's really 1-to-1 to the mapping to a power series. And you're also seeing that the even odd symmetries even Chebyshev polynomials have even symmetry, odd Chebyshev polynomials have odd symmetry. Not really big surprises so far. Now life begins to get more interesting because we actually want to do things with our Chebyshev polynomials. And the first thing we want to do is to actually figure out how to derive the coefficients of our Chebyshev approximation. So what we want to do is we want to write our u of x as a sum of coefficients times Chebyshev polynomials. Start at 0, and I'm not yet concerned about truncating series, so let's just put an infinity up there. And now to solve this for the UK, we're going to do the same trick that we did for the Fourier series. We are multiplying by a suitable second function, integrating over x, and because we have chosen a suitable second function, the t times the second function is collapsing down to a Kronecker delta, and that gives us then access to the coefficients. The suitable second function for Chebyshev polynomials comes about because of their orthogonality. And Chebyshev functions are orthogonal with respect to a weight function rho equals 1 over 1 minus x squared. So the identity that holds for Chebyshev polynomials is if you take two of them, tj of x and tk of x, and you integrate them multiplying by the weight function as well, dx, then we get a pi over 2 ck delta I delta jk. And the ck, this is one of these nasty little convenience numbers that unfortunately shows up. It's 2 if k is 0, and it's 1 if k is any other value. Okay, so the goal is to use this in our function up there. And so what we get is we need to multiply by tk times rho, and we then have the integral from -1 to 1 of u of x times, well, I have a tk up there, so I need the tj of x times rho of x dx is equal to, now I have everything on the right-hand side that I need. So this is a uk delta integral -1 to 1 dx. I have the tk von x because I already have it in the first line. And I'm getting the tj and the rho from here. And this is now no big surprise. Exactly our delta function, Kronecker delta, because this is how we have arranged this. And so we have a bunch of coefficients, pi over 2, Cj, u twinkle j. And that way we can get at the uj's. This is the continuous version of getting to the coefficients. But now we are playing again our Gauss quadrature grid with some associated grid points. So the associated grid points are xi equals cosine pi I over n minus 1. I goes from 0 to n minus 1. So these xi, if you plug in 0, you get cosine of 1. You get cosine of 0, which is plus 1. If you plug in n minus 1, you get cosine of pi, which is minus 1. So they cover the minus 1 to plus 1 interval just fine. And because this is also the Gaussian quadrature with weight rho, what this means is that we can express precisely these types of integrals very, very well. And it turns out that the continuous orthogonality relation is turning into a discrete orthogonality relation. That if you're taking the sum over grid points, so j equals 0 to n minus 1, this is the same as the integral over here. Now we need two of our Chebyshev polynomials, tk of xj times tn of xj. I need a 1 over cj bar here. Unfortunately, a few of these little nasty constants show up to deal with first and last terms. That this is equal to n minus 1 over 2 c bar n delta kn. So the same is true that multiplying two Chebyshevs together and summing over all the grid points gives us a orthogonality that the sum is non-zero when the two Chebyshev polynomials are the same, and it is 0 otherwise because of the Kronecker delta. The c bar n, well, it's either 2 or 1, and it's 2 for n equals 0 or n minus 1, and it's 1 otherwise. So, and now using this discrete orthogonality, we can finally write down what our transformations are. So, if I'm first talking about the transformations between the grid point values and the coefficients. So the first transformation is quite obvious, that the grid point value is, this is just the definition, uk tilde dk of xj. uj was as always, this is u at xj. And if we want to get u at any position x, what we do is we sum up our series. So this is going to be the sum of the coefficients times the Chebyshev polynomials at the relevant points. No big surprise so far. This now can again be written as a matrix multiplication, pjk, u trickle k, sum over k. And this pjk, well, is simply this one here. No big surprise. At the collocation points, the Chebyshev polynomials have some values. You put them all into a matrix, and then the sum over the spectral coefficients times polynomials turns into a sum over the spectral coefficients times the values of the polynomials at the various points. But what you're already seeing here again is a matrix multiplying. And I'm so far in the corner that I apologize. My writing is always also getting smaller again. This is the one part. We have a matrix multiplication that gets us from real space values from the coefficients to the real space values. For the opposite way, we're going to use our orthogonality conditions. So let's see how we do this. We start with this expression down here, and now we are multiplying it. Uj equals U tilde k tk of xj. And we have a sum over k already floating around. And now we are multiplying this thing by whatever we need in order to get to the discrete orthogonality. So let's see. I am putting, first of all, I need to make some more space here. Let me start over with putting space in the right places. So we have the Uj equals the sum over the U tilde k. K equals 0 to n minus 1. And we have a tk of xj. So this is the defining function of our series expansion. And now we're going to add everything else we need to make this nice. J, En of xj. We need a 1 over c bar j, 1 over c bar j. And we want to sum this whole thing over j. N minus 1. And this term here is now precisely the orthogonality, unless I have messed up, which I don't think I have this time around. So this is n minus 1 over 2 c bar n delta kn. And therefore, the entire left-hand side, is basically a constant times the un. And you can continue this line here, and what comes out of here is a n minus 1 over 2 c bar n u tilde n. So we have precisely our un on the right-hand side, and we can solve for it, and we can write un tilde equals the sum we have, j equals 0 to n minus 1, 2 over n minus 1 c bar n c bar j, en xj times uj. And if I'm calling this whole thing over here Snj, then we have the form of S Nj times Uj. So again, except for my very awkward looking summation here, we have a matrix multiply. If I want to write it without indices, I could write this as the vector of all the function values at our grid points is equal to the matrix S times the vector of all the functions at our grid points. And I must have messed up indices here. First of all, we are solving for the coefficients. And this is a K, and therefore the vector of all the coefficients is equal to a matrix times the vector of all the grid point values. So I apologize, today's lecture is unfortunately a lot of formulas that all look very similar to each other, and it's easy to get lost in indices. You see, I even get lost with my notes in my hand. I hope it gets better again after we are through this Chebyshev theory.
You have chosen axes on your Chebyshev modes. So if we use uniform modes, then there will be
So I've shown we are choosing here the Chebyshev nodes, and these are important. The reason these are important are there's a few different reasons why these are important. The first reason is that in order to arrive at the discrete orthogonality, we have been using Gaussian quadrature again. So we want to do Gaussian quadrature of this type of expression. And I've told you yesterday, if you use the right weights and the right collocation points, then you can evaluate this type of expressions exactly for polynomials up to order n, up to order 2n. Because each of the Chebyshev is at max order n, this thing here is at most a polynomial of order 2n. So if one is choosing the right Gaussian points, then we can evaluate this continuous integral without making any error at all. And that way we arrive at the discrete orthogonality relation without any error at all. So this mapping depends on having the right points. And then this discrete orthogonality went into our inversion here as well. Now we could say, okay, yeah, it's great you're doing all this fancy math here. Let me be much more simplistic. And well, we have our transformation that gives me the real space values as p times the spectral coefficients. Let me just define my capital S as p to the -1. That surely will work, because if I want to go back and forth with matrices and easily, I can of course just define it as the inverse. Then by definition, this condition will work no matter what grid points you use. But now the situation you run into is that the matrices S and P become increasingly ill-conditioned the further away your grid points are from being the good ones. And also, the further the grid points are away from the good ones, the worse the approximation gets. That means the worse the convergence goes and the exponential convergence is actually lost. And I have another piece, a little piece of a lecture snippet here to explain why the Chebyshevs are so nice. Perhaps I'm getting to this at some later stage, depending on how the timing works out. This is really crucial to choose the right points. Otherwise, the whole business, the whole house of cards falls together. Yeah.
The discrete orthogonality condition, so there should be rho xj.
No, there's no rho, because the way the Gaussian quadrature rules work is the integral of f of x times rho dx is the sum of the weights times f of xi. So the rho is ending up somehow in the weights, or rather the weights and the xi are chosen to already incorporate the role of the rho. And in this discrete orthogonality, the weights have somehow made it in as well, even if they're not spelled out explicitly anymore.
Okay. So if I try to come from this continuous orthogonality to the discrete orthogonality, so I see that there should be a factor of sine of pi I by n minus 1, and that is square root of 1 minus of x square, and that's why I think of that there should be rho xj. But and also the weight functions comes to be square root of 1 minus of x square. So I don't understand this condition, how it's derived. Actually.
Okay, perhaps we can talk about this after the class.
Sure.
So I think I'm missing uj in the solution. Utility.
That could be, yes, there's a huge chain missing here.
Sum over t and xj times uj.
So here we have this uj. And if we're now solving, the n minus 1 over 2 times cn goes here. And everything else should still be floating around here. So there is a uj here, yes. But this was not the question you were asking. Then let's talk about this after class. Okay, so we now have 2/3 of the puzzle in place. We have I need to move the uj again, because this uj is not part of my matrix. It's outside the matrix. We know the matrices that get us from real space values to coefficients. We know the matrix that gets us from coefficients to real space. And we know the grid points we should be using. And these xi's or xj's are the ones you need inside your matrices when you're evaluating the matrices P and S. The last piece of the puzzle that's still missing is, how do we now take derivatives?
What does the symbol of xi equals something like pi I? So associated grid points xi.
Xi equals cosine of pi times I over n minus 1. Okay, so where am I with writing? Let's start here. And I'm probably needing some of these expressions again, but I'll see it when we get there. So to take derivatives, we will exploit a recurrence relation. So there is a recurrence relation between the derivative of the k plus first Chebyshev polynomial the derivative of the k minus first Chebyshev polynomial, and it turns out the difference between these two happens to be 2 times tk. So now let's write down our Chebyshev series for the derivative 2 times. The first time I'm writing down is just the usual one. You have a series first without the primes, and then if I take the derivative of this series left and right, the primes show up because we're doing an x derivative. But now I also want the series to have the form of a Chebyshev series again with some new coefficients. And just because there's so many tildes showing up in the next few lines, I will remove the tildes and not bother about the tildes for this part of the calculation. And what we want to do is we want to find the relation between the UKs, the coefficients of the original data we came from, and the UK prime, which would be the coefficients of the series for the derivative. Such a relation must exist because if I'm summing up to k equals n, or n minus 1, then the Chebyshev polynomials are all polynomials, so we only have polynomials up to order x to the n minus 1. If we take a derivative, we get polynomials up to order x to the n minus 2. And so our original polynomials will certainly be good enough to represent this. We still have enough degrees of freedom to recover all these polynomials. So something like this must exist, and we want to find it. Okay, let's substitute in our recurrence relation. And it turns out the best way of doing it is to taking this tk here and substituting our recurrence relation in. Out comes the sum over k of uk prime 1/2 tk plus 1 prime over k plus 1 minus 1/2 tk minus 1 prime over k minus 1. And now let's change the sum. Sum over k goes into sum over k plus 1 and sum over k minus 1. So it will become clear in a second. For this first term here, I'm changing k to k minus 1, so that if in the first term we have a tk prime over k 1/2 uk minus 1 prime. I'm just changing the label k, subtracting 1 from it. In the second sum, I'm also changing the label k, but this time I'm adding 1 to the k so that I have tk over k 1/2. And now this uk turns into a uk plus 1. Sorry, what was the question? And the reason why I did these renamings of the case is that if I'm now collecting the terms here again, I have sum over k. At the end of it, I have a tk prime. And in the middle, I have a uk plus uk minus 1 over 2k minus uk plus 1 over 2k. Let me double check. I hope this is right. And the point is that I now have on the right-hand side here a sum over tk prime. And on the left-hand side, I also have a sum over tk prime. So we will be able to equate the coefficients. And now there was a question.
I'm not getting, you are replacing a sum by k plus 1, k minus 1. So why still k is there in the sum? So in the last line, you are replacing all the k's in terms of either k plus 1 and then the second k minus 1. But now still you are using sum as k. So why so?
I should be starting one higher or one lower. You're absolutely right. Let's see how this turns out. Let me chicken out of this and say that one suitably takes care of the edge cases. I'm not doing the edge cases here correctly, I agree. But let's just gloss over it and let me promise you that they can be done correctly. And disregarding this little thing, and actually the little thing will show up in a little while, what we now have is that we have that this uk over here must be equal to uk minus 1 prime over 2k minus uk plus 1 prime over 2k. And if we now solve for UK minus 1 prime and take into account proper account of k equals 0 and 1, which I didn't do, then what comes out of this is that ck minus is that uk minus 1 prime is equal to 1 over ck minus 1 times uk plus 1 prime plus 2k uk. So most of this expression is obvious. This is this one here multiplied by 2k and moving the uk plus 1 to the left-hand side. Yep. And the 1 over ck here, this comes precisely from looking at k equals 1 and 2. So, and this puts in that you have C0 equals 2 and ck equals 1 for k greater equals to 1. So that coefficient actually comes in when you take care carefully about what happens at the lowest k. Okay, so we have this funny looking expression. I'm putting back the tildes now for correctness. And how does this expression now help us? So, to use, so we have given some coefficients uk of our favorite function. And now we can play the following game. We first set un minus 1 delta to 0. And this is 0 because the derivative of x to the n minus 1 prime is x to the n minus 2. And therefore, we don't have any x to the n minus 1 terms left over in our derivative. We also set un tilde to 0. And this is purely convenience. And this is also true because we never had a term with t capital N in it. So its coefficient is 0. And now we can loop from large k down to small k. And we can compute, how to do this on the next page. We can compute our kth coefficient with the magic formula I have in the blackboard over there as 1 over ck times u twiddle k plus 2 minus 2k uk. So if you start at n minus 2, then the u tilde k plus 2 is higher. We already know that. And as we go down, we always only need higher order terms of this derivative expansion. So we can always evaluate this right-hand side here. And what this is, it is a recurrence relation. And this recurrence relation gives us from the UKs, the UK primes. And as I will show you in a little while, this recurrence relation can also be expressed as a matrix. So we can write the coefficients. We can write the U delta prime K as a matrix D delta K J, U delta J. And at that point, we are back down to the situation that we have everything as matrices. And so we have, I've erased this, I believe, but now we have the major operations we have U delta equals S times U real. We have U real equals P times U delta. And we have again the derivative at the grid points, U prime, equals as a function of the original U at the grid points. We can do the S to get to physics, to spectral space. We can hit it by the D matrix. And we can go back to real space with the P. And so this is a D matrix acting on all the grid point values. So this has been quite a bit of formalities today. I apologize, but unfortunately, we need this to make progress and then do the fun stuff starting tomorrow. But I think at this point, I'll first wait for a minute, giving you the chance of asking questions, and then I have a small demo. So where is Zoom? Share screen. Okay. And so how this is going to work when all the dust settles is as follows. One can write a function that takes n, the number of collocation points, and that returns x, the collocation point values. It returns the matrix 2 spec, which I'm calling S on the blackboard. It returns the matrix 2 phys, that I'm calling P on the blackboard. And it returns this matrix D, the first derivative matrix, and a similar one for the second derivatives. And so you can put all this in a functional that computes all these things, nice and smooth. And now we have a little test here. We're starting out with a Lorentzian for a change, 1 over 1 plus x squared. And this line 5 evaluates this Lorentzian and all the 8 grid points that are stored in X. So we have U at the grid points. And then we can compute the derivative of this function by matrix D1 multiplying U by a matrix multiplication, which in Python is indicated by the at symbol. And then I'm plotting it, and this is what comes out. The blue line is the Lorentzian, awfully underrepresented because I only have 8 points. The orange line is the derivative of the Lorentzian, awfully underrepresented because we only have 8 points. But if I'm now going back and putting back more resolution into my output by taking the same Chebyshev series that only has 8 terms and evaluating it on a wayfinder grid with 200 points, I can do this by, well, I compute the spectral coefficients by multiplying S times U, and then having the spectral coefficients, I can sum up the series by coefficient times Chebyshev polynomial, cosine of k times arc cosine of the grid point x fine. And that way I get an interpolated version of my 8 basis functions Chebyshev polynomial. And this is how it looks like. It's actually very neat, the Lorentzian. And if I'm taking the difference between the interpolated one and the exact Lorentzian I started out with, well, the difference is sitting down here at 0. And in order to see this, what this actually is, this difference, I have to multiply it by 100. And so you see that the difference is actually 0.2% at peak. So all these matrices actually do something useful and everything fits together. And I think with this, I am out of time. So I'll close here.